back. And now let's talk about convolutional neural networks, which are a subset of artificial neural networks that focus on images. So imagine that we want to create a deep learning classifier that is sensitive to variations between different types of things, but not sensitive to things like changes in viewpoint, changes in illumination, scale, deformation, occlusion. You know, half a cat is still a cat. Messed up cat is still a cat sitting on a pattern that looks exactly like the cat is still a cat. And well, this is not cats, but all these different chairs are still chairs. Convolutional neural networks are really what you want to use to do image classification like this. And they're a pretty new idea. So Jan LeCun built GoogLeNet in 1998, and that's pretty much the first recorded use, first published use of a CNN. But it was in 2012 that a bunch of researchers built AlexNet and just crushed it. And this is a really groundbreaking paper and really fascinating reading. The ImageNet competition, the ImageNet dataset is this gold standard labeled dataset against which researchers will train and test their classification models. So even as late as 2011, the best performing image recognition models at the time were still committing errors at the rate of 26-27%. So it really was a bit of a we really passed some milestone in 2012, 2013, where CNNs took the error rate from almost 30% and down to now the best performing image recognition models actually do better than a human now. More or less, when you get a human to classify these images, they still get things wrong 5% of the time. So why use a convolutional neural network? Why use a different architecture instead of just continuing to stack more and more layers on the type of fully connected deep learning network that we've been building for the last couple of segments? Yeah, we can do that, but it's hugely expensive. And the reason why comes down to the number of parameters that pop up in images. Take this image of a cute dog. Imagine that it is 32 pixels wide and 32 pixels high. It's 32 hypothetical pixels wide and high. And it has 3 color channels for red, green, and blue. A single fully connected neuron will have 32 times 32 times 3, 3,000 parameters. And this is for an image that's 32 pixels wide. Most high quality photos are about 1,000 pixels wide and high, and so imagine how that would stack up to like 1 million parameters to train on. And the more parameters you have, the bigger your model has to be, the longer training time takes. And this is not necessary to build a high performing model because unlike the features we've been working with, the image has a structure to it and a hierarchy to it that we can use to build something smarter. We can train a less dense learning model on these. So a convolutional neural network is a specific subtype of deep learning that assumes that all inputs have this like structure to it. There are many different subtypes of neural networks. If you're working with language or sequences, you'll want to learn more about RNNs. We've chosen to focus on CNNs for our mini workshop because this will let you practice working with bigger volumes of data in the cloud environment. Image data is typically exponentially bigger than text. And we're using a classifier instead of a regressor because it's just cleaner for your learning. It gives you scores of did you classify this correctly or not, versus if we were to work with a language and sequence model where it would generate more sequences. They're kind of fun. People use them to build chatbots, but you can't score them as easily. You can't like build a benchmark for yourself and try to beat yourself. So what are we going to cover in this segment? We're going to cover how CNN architectures are built. We're going to talk specifically about 3 layers, the convolution layer, the pooling layer, and the fully connected layer. We're going to go through 2 famous CNN architectures and then switch to hands-on, more practical work, explaining how TensorFlow layers work and how to set up the CFAR10 classifier on Google Cloud Platform so you have like a nice working end-to-end image classifier. Okay, so let's start talking about the typical architecture of a convolutional neural network. So first, a convolutional neural network has layers that are distinct and feed into each other. So the convolution is a layer, pooling is a layer, the nonlinearity / activation function is expressed as a layer. Second, it passes activation volumes through each layer. So think of each layer kind of as a function or as a node in a TensorFlow graph, where you take data in the form of an activation volume and you keep passing and transforming those volumes through each layer, where the very final layer you have is a 1 by 1 by n layer, where n is the number of labels that you are training this image classifier on. So unlike the other types of neural networks, CNN architecture, if you draw it out for yourself, there's a very distinctive squish pattern where you will never have an activation volume that is larger on this end than it is on this end, because of the nature of the squishing into the prediction layer functionality. What is an activation volume? This is the key concept for CNNs. A layer takes in an activation volume of parameters, so think of it as our weights in earlier lectures, and outputs another volume of parameters, and so that's a new activation volume that it passes into the next layer. Activation volumes have width, they have height, and they have depth. So think about what the very first activation volume going into a CNN is. That would be the image width, height, and channels. And let's see how the activation volume is defined by going through an example of a convolving motion. All right, so let's look at this, our dummy image with our puppy with 32 hypothetical pixels wide, that's 32 hypothetical pixels high, and has a depth of 3 for the 3 color channels, red, green, and blue. So not this specific image, but the volume in which you feed in all the images into has a volume of 32 parameters by 32 parameters by 3 parameters. Okay, so next let's talk about convolutions. To start, a convolution is the second key concept in CNNs. And we start by thinking about filters first. So what is a filter? It's a single feature detector that you're searching for through the image. Filters are randomly generated. They pass over activation volumes, and as they pass over these volumes, they're trained to recognize different features. Where early activation maps respond to simple elements, and this is why the convolutional neural network takes advantage of hierarchy. For non-hierarchical data, you can't actually do something where early activation maps respond to single elements and later activation filters operate on top of the previous layers. So even though they're the filters are all equally quote-unquote simple, what they come up with gets more and more complex because the activation volume that gets passed from one to the next gets more and more processed. So the deeper into the CNN the layer, the more complex the features that the activation layer recognizes. The insight for this is thinking about how humans go from recognizing blocks to patterns to more and more complex shapes. That's kind of how you can think about what filters get trained to recognize at each layer. So filters are also mathematically, they have to be three-dimensional as well, but they have a width and a height that is smaller than your activation volume because they pass over your activation volume. So now that we have a rough sense of what a filter is, let's figure out how to use a filter to generate an activation layer. So let's take a 5 by 5 by 3 filter and overlay it on top of our cute puppy image. What we do is we take the filter, we multiply it against this region of the puppy picture, calculate the dot product, and use that first value as the first entry in the activation layer. And then what we're going to do is we are going to move the filter one step from its initial position, and given that images are only two-dimensional, there's only one or the other way you can go. And the step you take, this is called the stride. So if you use stride equals 1, you will have 1 pixel width here, and everything just, you move your filter window over by stride 1. So almost everything is something you've processed over before, and just this piece here is new. You multiply the dot product again, move it a step, calculate the dot product, and so on and so forth until you have convolved the filter across the entire image. And then you have an activation layer. Here you end up with that activation map with dimension 28 by 28 by 1. Why is it 28? Because if you take a filter of width and height 5, I really can't say that word, height 5, and multiply it across, you'll get an activation map like this. And mathematically, you will always get an activation map with dimensions smaller than the original volume. Take a moment to think about it. So what is the biggest possible activation map dimension you can produce? If you have a filter that is 1 by 1 by 3, then you will have an activation map that is the same size as the volume you have fed into it, but you'll never be able to generate one larger. Okay, so the key thing to note with the activation maps is that all the neurons in the activation map are sharing weights and biases. Because remember, you're passing the filter and you're taking the dot product on each filter times region. So they really are sharing a lot. There's like a very high overlap in what they're training on. So it kind of counts as an ensemble method. And remember, it's ensembling because we're taking advantage of the hierarchy in images. So we're calling when one filter equals one activation map, but does not equal, one filter does not equal one activation volume. An activation volume consists of many different filters. Because think of it this way, each activation map is training on the same, to recognize the same visual feature, just at different regions in the input layer. So if you want to train your CNN to recognize different features, you have to generate different filters. So one filter equals one kind of visual hierarchical feature, and you want to have many layers, and so you want to have many layers in each convolution layer. So let's say we have 3 filters. Let's kind of run through this example. For every filter, you will convolve it across the image and generate one activation. Ooh, this says layer, but it really should just say slice or something like that. So each one of them, we take the dot product of the second filter, you generate this dot product, you convolve it across. Third one, you generate the dot product of this, you convolve the whole thing across. And as you go, you will actually be training each layer almost separately. So you will have 3 activation layers that you will then stack on top of each other, and that will form the activation volume to pass through the next layer in your CNN. Okay, so let's talk a little bit more about stride. Just to remind you, we take our original image, we take our original hypothetical image with volume, with dimensions of 32 by 32 by 3. And earlier, we've been assuming that you take a stride of 1, a step of 1 when you convolve. So this is a sample filter, dimensions 5 by 5 by 3. You map it, you generate the activation layer. But what happens if we, instead of using a stride of 1, we move the filter 2 steps away from its initial position? In this situation, you can do that. You can calculate the dot product. Think for a moment about, will the activation layer in this condition have the same dimensions as the activation layer when we use a stride of 1? So we have now convolved to this point, the 26 mark. But we hit a problem. If you take a step of 1, you will nicely cover the space and be able to multiply and get a correct value for here. But what happens if you take 2 steps is that your filter is now hanging over the image volume. What do you do in this case? Surprisingly, the answer is pretty simple. You do zero padding. Zero padding is as easy as it sounds. You take an image volume and you pad the edges with zeros to just allow the math to work out and to not explode in your face. So there you go. Now the filter fits. You do your multiplication. You're able to generate your activation layer. And to answer our previous question, if you take bigger steps, you will do fewer multiplications, which means your activation maps are of smaller dimensions, but of the same depth. So in this case, if you take the same filter and the same image volume, but you increase the strides from 1 to 2, instead of a 28 by 28 by 3 activation volume that you're passing along, you're now passing along a 15 by 15 by 3 volume. And that brings us to some of the basic constraint math around convolutional neural networks. So this is, in practice, it's really easy to mess this up, but it's quite straightforward math. There are dimensional constraints involved in the choices of these 4 hyperparameters that we've been speaking about. First is the number of filters you have. Second is the dimensions f you have. Third is your choice of stride as you convolve. And then fourth is your choice of whether you have zero padding and how much zero padding you have. Think for a moment about the dimensions of any volume that passes through a convolution. Any convolutional layer will accept some volume with the width and height and depth, and it'll output a volume with this, and this with height and depth. So we linked here for a breakdown of how this math works out. It's really straightforward algebra, really. And the rule of thumb is if you are trying to build your own convolutional neural network and just want to use something that works generally well, you want to use an f of 3, stride of 1, and a padding of 1. And then how many filters should we have? So that's a big question. Roughly, a filter is a single feature detector where a feature might be, there's a straight line here, or there's a curved line here, or there's a double curved line here. So realistically, we want as many filters as we can stuff into the model. Realistically, it depends on how visually complicated your model is. And realistically, it is limited also by your computational capacity. So that means that you need to treat it as an hyperparameter to optimize. The more features you have, the more compute you need, but also the more complex the more complex your model can get. Here's the second type of layer. So we've gone over the convolutional layer. Now let's look over the pooling layer. So what is pooling? Pooling is that squish function that downsamples a volume into a more manageable size. So earlier we saw how your choice in stride could squish down your activation volume. You can do the squishing without filters by using a pooling layer. So intuitively, think of this slice, and if you have a max pool layer with 2 by 2 filters and stride 2, so you have a filter that's this high, this wide, takes a stride of 2, then you will end up with this. And this is max pool. So max pool takes all the pixels, gives you the maximum within all the features, gives you the maximum value. So here it's 6, here it's 8, here it's 3, and here it's 4. Max pool is highly recommended as you're downsampling. There's a couple other types of layers that will do downsampling, but max pool is highly recommended. There's also average pool, which does exactly what it says on the tin. Now, think about what happens to the image. it gets a bit more pixelated, really. But max pooling, because images are very hierarchical, you're not losing that much information with a max pool. This works shockingly well for images, not so well for other things. So now let's talk about our fully connected layer, and this should look very, very familiar to you. In CNN architecture, a fully connected layer is also called the dense layer. No surprise, this is a DNN. This is exactly the same as a fully connected deep neural network layer. The final layers in a CNN are fully connected. The first layers in a CNN, you don't want them to be fully connected because you then run into that problem we talked about, which is too many dimensions. So once you've downsampled enough, once you've pooled enough and run convolutional layers through the model, it now gets to a size wherein this dense layer, this FC, is manageable from a math perspective. And ultimately, you want your very final activation volume to be 1 by the number of classes, and that is a fully connected layer. So the very final layer in a CNN will almost certainly be a fully connected layer. So ultimately, just keep this in your head. You want a sideways pyramid of shapes where the width and height decreases and dimension decreases as your activation volume moves from input into your prediction layer. Great. Now let's look at two famous layer architectures. So there's many different ways to stack and mix and remix these things. It's not always a straightforward layer. We'll see with inception. The interesting thing about CNNs is that you don't really need to reinvent the wheel and retrain a classifier. One really weird, awesome thing about CNNs is that you can pop off the final prediction layer of an existing convolutional neural network, and you can train a different, you can add layers on top of somebody else's pre-trained CNN. That is super duper cool. Here are instructions on how to do this on top of the Inception v3 CNN that Google has built and shared using TensorFlow. This is called transfer learning, the process of taking an existing CNN, popping off that last layer, and training additional things so that it can recognize new classes. So this is the architecture for AlexNet. Recall that AlexNet is the 2012 convolutional neural network that really brought CNNs back into everyday use. This is actually very sensible. You take your model with 224 features, pixels, depth of 3 RGB, take an bunch of 11 by 11 filters with a stride of 4, push it in, max pooling, push it in, dense fully connected, dense layers, and then here you have the 1000 class predictions. These numbers are still pretty intense, but they were able to do this between 2 GPUs, and that's how they broke these things down. For more details, read the original paper. It's really interesting reading. This one, the competition for recognition, there's 8 layers in total here. There's 5 convolutional layers, dense layers. They applied the ReLU activation function across the output of all 8 layers and max pooling after the 5th convolution. This looked at 60 million parameters, used 2 GPUs, used a dropout of 0.5. And something interesting, and we will go over that later, is they took the original data set of images and augmented the number of images by a factor of 2048. Works pretty well, but with the thing with your data set, so here's something I just want to caution people on. When they are training their neural networks, the way these neural networks trains depends on what the human trainer, the person who originally labeled the images, think of as important. Look at this picture. I think Dalmatian is quite a good tag to put on it, and that is what the convolutional neural network decided. But the correct tag is actually cherry, because when somebody was assembling this data set, they thought that the cherries were more important than the dog. Pro tip, don't blindly train models. It is absolutely worth it for you, the human, to do this thing called actually looking at your data. So, one weird trick to 1000x your training data. Many of you might be working with data sets where images are pretty rare. For example, if you have an image of a broken cell site and you're trying to recognize a cell tower, and you're trying to train a CNN to recognize broken cell towers, what do you do if you only have 100 pictures of different types of broken cell towers? With images, you can actually at least 10x your training data set by, guess what? Rotating each images by 10 degrees, zooming in and out of the filters, adding Instagram filters on top of it, misaligning the image. Read this paper by Krzyzewski, pretty funny paper. It has some more tricks for parallelizing the implementations of these two. Do keep in mind, CNNs don't learn to see images the way humans see and interpret images. They're really learning their own thing. So these tricks wouldn't work for us as people, but they work really well for CNNs. Between 2012 and 2014, huge advancements in processing power, in people's understanding of convolutional neural networks. So this is the GoogLeNet Architecture. In the time between 2012 and 2014, the computer scientists got really sophisticated about how they build these models, to the point where this is the architecture of GoogLeNet, much more complex than AlexNet. This won the ILS-VRC in 2014. Funnily enough, it uses 12 times fewer parameters than AlexNet, and it represented the first really effective use of one-by-one convolution filters. Think for a second, what is a one-by-one convolution filter? It is a filter that takes in one activation volume and outputs another activation volume of exactly the same dimensions, or like width and height dimensions at least. While they didn't provide the specific details about how many GPUs, this trained on a quote-unquote few high-end GPUs within a week. And this is the basis of the whole Inception family of convolutional neural networks that is public for public use by Google, and so a lot of people use that to do transfer learning. What's going on inside a volume? It's how can you know? So earlier we were talking about how each filter trains on a feature, and as you move through the architecture of a neural network, a convolutional neural network, it recognizes things that are more and more complex. But what exactly is it recognizing? How can you introspect and eyeball this layer? If you're curious about that, the most cited paper on introspecting a CNN is this paper by Zeller and Fergus we've linked. This methodology is also used by Google's Deep Dream to kind of reverse out, to use these layers, to use these activation volumes to kind of show you what the computer is quote-unquote dreaming about. So this is a snapshot, sorry for the pixelation, but this is a snapshot from this paper here, where this shows what pieces of this image most excited the activation volumes. So for dogs, look at how much a nose is indicative of dogginess. It's actually pretty interesting here. If you had a cherry with 2 eyes, would it recognize it as a dog? Maybe we need a tongue on top of it too. But still, an active area of research, introspecting AI in general and looking at CNN activation volume specifically, is an active area of research to work on. Okay, now let's look at layer architecture, and let's learn a little bit of TensorFlow so we can understand how to implement these things. Now take a look at this drawing of an input layer, a fully connected layer, and an output layer. What does this do? This will give you, if you trained 3 layers like this, it will give you this is actually an implementation of the linear classifier WX plus B that we implemented very, very early on. How about this? Takes an input layer, a fully connected layer, puts an activation function on top of the next fully connected layer, and gives us output. this is a 2-layer neural network with one hidden layer activated by ReLU. And now here's a very common convolutional net pattern. You take some input, you run it through a ReLU layer, a convolutional layer, and a pooling layer, a max pooling layer. You repeat this until you're happy, and then you feed this whole thing to ReLU on top of a fully connected layer, because remember, dense layers or fully connected layers should come towards the end. Cycle, like run many iterations of this until you're happy, and then output, run it through one last fully connected layer as your output set of labels. How do we do this on TensorFlow? So the reason why we want to think of implementations in that level is because there is a layers API that exists between the core API and the estimator API that we've built earlier. Earlier in some of our sample code, we show you how to implement a simple graph in TensorFlow core Python. You have to define everything here. You have to define every node, every tensor. At the estimator level, things become actually quite surprisingly easy. We were able to implement a deep learning network with just 2 or 3 lines, really. In between this exists the layers layer. And on top of everything, if you actually want to use Keras, which is even simpler to use in many ways than the estimator layer, you can do that. So you can do everything that you can do here in the estimator level. You can implement it as a layer. A layer can include operations, like we were seeing how you can implement ReLU as a layer. You can implement a lot of the things we were talking about earlier, the Xavier initializer, regularizations, convolutions, pooling, and ReLU as layers. So here's a mystery to encourage you to read the documentation linked here. ReLU is both a layer and an activation inside a convolutional layer. How is this implemented and how is this expressed in TensorFlow? As an exercise, so this is this is on our GitHub repo also. Take some time to download the MNIST convolutional neural network code from GitHub and examine the structure. Look at how they put together the layers. So this is actually pretty straightforward. CNN and we have, for our example on GitHub, stripped it down to just the layer elements.